In this video, we'll talk about the graphs of logarithmic functions. The function f of x equals log base b of x is defined to be the inverse of the exponential function having the same base. And so the graph of the logarithmic function is the reflection of the graph of the exponential function through the line y equals x. There are two types of graphs for exponential functions depending on the base, whether it's bigger than 1 or between 0 and 1. And so the same is true for logarithmic functions. First, let's take a look at the case where the base b is greater than 1. The exponential function is seen here. It has a horizontal asymptote at y equals 0. And the graph approaches 0 as x goes to negative infinity, that is, as x goes to the left. But it increases very rapidly as x goes to the right, going to infinity. If we reflect this curve through the line y equals x, we get the graph of the logarithmic function with base b. Most of the properties of the logarithm we can observe based on these graphs, knowing what we know about the exponential function. For example, the domain of the logarithmic function is the set of all positive numbers. That's because that is the range of the exponential function. Similarly, the range of the logarithmic function is the set of all real numbers, because that's the domain of the exponential. The x-intercept is the point 1, 0. That's because the y-intercept of the exponential function is 0, 1. If you reflect through y equals 0, you swap the roles of x and y. The logarithmic function has a vertical asymptote at x equals 0. That's the y-axis. So the y-axis is a vertical asymptote for the logarithmic function. The logarithmic function has the vertical asymptote x equals 0 because the exponential function has the horizontal asymptote y equals 0. The x-axis is a horizontal asymptote for the exponential function. As you can see, as you move to the left, the curve gets really close to the x-axis. That's because the exponential function goes to 0 as x goes to negative infinity. So we have this horizontal asymptote. We have this horizontal asymptote for the exponential. But if you reflect the curve, the exponential curve, y equals b to the x, through the line y equals x, to get the logarithmic curve, y equals log base b of x, if you reflect the curve y equals b of x through this line, you also have to reflect its asymptotes. And so its horizontal asymptote needs to be reflected as well. But if you reflect this horizontal asymptote through the line y equals x, you get the vertical one. That's why the y-axis, or x equals 0, is a vertical asymptote for the logarithmic function. So x equals 0, that's the y-axis. We have something that we'll call a key point on the graph. That's the point b1. When x is equal to b, y is equal to 1. That's because if you plug in b into the logarithmic function, log base b of b, you get 1, because 1 is the power of b that gives you b. This also corresponds to a point on the exponential curve. Namely, this corresponds to the point right about here, which is the point 1, b. Because in this case, if y is equal to b to the x, if x is 1, you just get b as a result. It's important when you're graphing to look for the key point because it will help you graph the curve. Let's talk a little bit about the end behavior of the logarithmic function, or the logarithmic curve. As x goes to the infinity, as x goes to the right, the logarithmic function increases without bound. So log base b of x goes to infinity as x goes to infinity. Moving to the left, x can't go to negative infinity because the domain of this logarithmic function is 0 to infinity. So the most it can do is go to 0. And what happens to the logarithmic curve as x goes to 0? As you move to the left, as x moves to the left, the curve decreases without bound. So log base b of x goes to negative infinity as x goes to 0. It goes to negative infinity. Notice that we have x approaches 0 plus. Remember that that plus means that we're approaching from the right. So this symbol means that x approaches 0 from the right. It has to approach from the right because there is no curve to the left. The domain does not include negative numbers, so you can't approach 0 from the left because you're not allowed to put negative numbers into the function. You should think of this 0 plus as saying that x is slightly bigger than 0. So x approaching, let me try that again, x approaching 0 plus, that means that x equals 0 plus something. So you should think of it as being slightly bigger than 0. So it's slightly bigger than 0 and going to 0, getting smaller. As that happens, the curve just decreases without bound. Goes to negative infinity. So this is the case 1 where, oh, that's not supposed to be here. This is the case 1 where b is greater than 1. Case 2 is where b is between 0 and 1. Now, most of the properties are the same in this case, except the end behavior. So in this case, when b is less than 1, but positive, we're always talking about bases that are positive. So if b is between 0 and 1, the exponential function demonstrates exponential decay. So in this case, you have most of the same properties of the other exponential. The only difference is now, as x goes to the right, the exponential function decreases and decays to 0. Notice it doesn't go below 0. Exponential functions are always positive. But if b is between 0 and 1, then it decays, getting closer and closer and closer to 0. Because the x-axis, y equals 0, is a horizontal asymptote. On the other hand, if you're looking at this exponential, let me just label it. Y equals b to the x is the exponential. This is the exponential here. As x moves to the right, it's going to 0, but as x moves to the left, this curve shoots up to infinity. Now, if we reflect y equals b to the x through this axis, which is again y equals x, we get the logarithmic function. Let's label it down here. Y equals log base b of x. Now this has all of the same properties for the most part. The domain is still the set of positive numbers. You still can't put a negative number into it, and the range is the set of all real numbers. That's because the domain of the exponential is the set of all real numbers, so that means the range of its inverse is all real numbers. And you can see that from the graph, that it's going up to infinity on the left and down to infinity, to negative infinity on the right. So the x-intercept is still the same. The x-intercept is still y comma 0. That's because the exponential will always have, the exponential y equals b to the x will always have y-intercept 0 comma 1. I lost a little bit of the parenthesis here. Let's just put that back in. So the x-intercept of the logarithmic function is still 1 comma 0. And that's really just saying that the power of b that gives you 1 is 0. b to the 0 is 1. We still have a vertical asymptote at x equals 0. That's again because the domain is 0 to infinity, and as x moves closer to 0, you get explosive growth going as x goes to the left. We'll talk about that in a second with the long-term behavior. The key point on the graph is still the point b comma 1. It's just now b is between 0 and 1, so this point, b comma 1, is to the left of the x-intercept. If we scroll back to the previous slide, which I'll do now, In this case, b was greater than 1. So you can see that the key point has x-coordinate b, which is greater than 1, so it's to the right of the x-intercept. But now if we go back to the current slide, now we have b between 0 and 1, and so you can see that here. B is between 0 and 1. It's to the left of our x-intercept. The key point is always the point where the y-coordinate is 1. So when you're trying to graph one of these things, you want to find the coordinate that corresponds to the x-coordinate that corresponds to the y-coordinate 1, and that's your key point. We know that there's always such a point because the range is going to be from minus infinity to infinity. So that means there will necessarily be some point that gets you 1. The end behavior of this logarithmic curve when b is between 0 and 1 is given here. Log base b of x goes to negative infinity as x goes to infinity. So as x moves to the right, the logarithmic curve decreases without bound. And as x moves to the left, it goes up to infinity. Now again, when the furthest to the left x can go is 0. So as x approaches 0 from the positive side, or from above, from the right, the logarithmic curve increases without bound. So log b, or log base b of x, goes to infinity as x goes to 0 from the right. So once again, just like before, this means that x approaches 0 from the right. There we are. So the rest of these slides are going to be devoted to drawing graphs, but what do we look for when we're drawing graphs? So when we're graphing a logarithmic function, the things we want to do is we want to determine the domain, the range, the x-intercept, the vertical asymptote, and the key point. Once we have all of these things, that will help us graph the logarithmic function. So perhaps as a little bit of practice to identifying the domain, let's do it on these examples here. So this is our first example. Identify the domain of each of the following logarithmic functions. So the first example, f at x is equal to log of x plus 1 minus 100. Now really, when you're talking about the domain, the only thing that matters is what's inside the argument of the logarithm. You have to make sure that that's positive. So in order to identify the domain, we just need to be sure that x plus 1 is strictly greater than 0. Because you're not allowed to put a negative number or 0 inside of the logarithm. The fact that we have a minus 100 here does not affect the domain at all. The only thing that matters for this problem is that x plus 1 has to be greater than 0. That's the only thing that matters for the domain. So in other words, x is greater than negative 1. So in interval notation, the domain is the set from minus 1 to infinity. We're not including the endpoint, because if you plug in x equals 1, you get 0, and log of 0 is undefined. Okay, let's move on to b. G at x equals log base 2 of 2x plus 6 quantity, and then to that we add 5. So again, we don't really care that we're adding 5 here. That doesn't affect the domain. The fact that this is log base 2 also doesn't affect the domain. The first example was log base 10. This is log base 2. The base of the logarithm doesn't affect the domain. You always just have to be sure that the argument is positive. So 2x plus 6 needs to be greater than 0. So we just need to solve for 6, or solve for x, so to speak. I said 6 because the first thing we're going to do is subtract 6 from both sides. So then we have 2x is greater than negative 6. Now we divide by 2. So we'll have that x is greater than negative 3. And so that gives us the domain. So the domain is the set of all x's such that x is greater than negative 3, which in interval notation is negative 3 to infinity. Alright, we have one more that we want to look at. H at x is 1 minus the natural logarithm of 5 minus 2x. So natural logarithm That's log base e. But again, the base doesn't matter. The fact that there's a minus sign in front also doesn't matter, and this 1 doesn't matter as far as the domain is concerned. The behavior of the graph will change because of this minus in front of the logarithm, but we're only interested in the domain. So the domain is where the argument of the logarithm is greater than 0. So 5 minus 2x greater than 0. So I'm going to add 2x to both sides, and so that's going to give me that 5 is greater than 2x. So now we just divide by 2, and we get that 5 halves is greater than x, or, if you prefer, x is less than 5 halves. So in that case, the domain is now the set of all x values such that x is less than 5 halves. So that means it's negative infinity to 5 halves, not including the endpoint. So notice now that the domain includes all of the negative numbers. That's because of the minus sign in front of this 2x. All of these negative numbers, and then positive numbers up to 5 halves, will ensure that 5 minus 2x is a positive value. The x might be negative, but 5 minus 2x, the argument of the logarithm, that will be positive. In this example, we want to use the graph of y equals log base 3 at x, which is what's given here. Y equals log base 3 of x. We want to use this to graph y equals log base 3 of x plus 4. Now, really, this is just the graph that you already see here, just translated to the left by 4 units. So we could really just do this by tracing this graph and then moving it over 4 units. So we could do that, but let's be a little bit more careful about it. So we're going to find the items that we were told to find. Let me just scroll back up here. So when graphing a logarithmic function, determine the domain, the range, the x-intercept, the vertical asymptote, and the key point. So we're going to find all of these things and use those to help us with the graph. Okay, so what about the domain? Well, the domain we know how to find now, because we want to just make sure that the argument of the logarithm is strictly positive. So that means we want to make sure that x plus 4 is greater than 0. So that means that x is greater than negative 4. So the domain is the set from negative 4 to infinity. So that's starting here and moving to the right. Now, what this will tell us is that we have a vertical asymptote right here at x equals negative 4. We'll write that down in a second. First, let's talk about the range. The range is the easy one. That's negative infinity to infinity. Because the range of a logarithm function like this is always going to be negative infinity to infinity. All right, the x-intercept, not the x-intercept, I mean the vertical asymptote is x equals negative 4. So we have a vertical asymptote here at x equals negative 4. Why is that? Well, that's because the domain goes from negative 4 to infinity. Everything's shifted over by 4. So the graph that we see here, y equals log base 3 of x, that has a vertical asymptote at x equals 0. And everything's shifted over by 4. So that's why the endpoint of the domain here, negative 4, will give you a vertical asymptote. Okay, so what we now need is the x-intercept. The x-intercept is where y is equal to 0. Okay, so we're just going to look at this equation and we're just going to put y equals 0. So 0 equals log base 3 of x plus 4. So if we convert this into an exponential, what does this tell us? 0 is the power of 3 that gives you x plus 4. So 3 to the 0 gives you x plus 4. But 3 to the 0 is 1. So 1 equals x plus 4. And subtract 4 from both sides, and you'll get negative 3 equals x. So the x-intercept happens when x is negative 3 and y is 0. So that's right about here. So that's the x-intercept. The next thing we want is the key point. The key point is where y is equal to 1. So 1 is equal to log base 3 x plus 4. Again, what does this mean? It means that 1 is the power of 3 that gives us x plus 4. So 3 raised to the 1 is x plus 4. Or in other words, 3 is equal to x plus 4. Subtract 4 from both sides, and you get negative 1 is equal to x. So our key point has x-coordinate negative 1 and y-coordinate positive 1. So it's minus 1, 1. So that's right here. That's our point. So what we know is that we have a vertical asymptote right here at x equals negative 4. We pass through the point negative 3, 0 and the point negative 1, 1. What else do we know? We know that as x goes to the left, it's going to negative infinity, and as x goes to the right, the y values are going slowly to positive infinity. So you'll notice that this increases quite slowly. It's increasing, but it's very slow. It's not flat, but it looks almost flat. So we're just going to connect these like this, and it's going to look something like that. Now this is just a rough sketch of what it looks like. We can confirm that it looks something like this because I have the actual graph from a computer on the next slide, and there it is. So you can see it has the vertical asymptote at x equals negative 4. It crosses through the point where x is negative 3 and y is 0, and it also passes through this point right here, which is negative 1, 1. Negative 1, 1. And you can see it has the same overall shape that we thought that it would. Of course, my graph isn't as good as the graph of the computer, but it's not so bad. Let's do another one. Use the graph of y equals log base 2, which is given here. So this graph right here, this is y equals log base 2 of x. And we want to use this to graph this thing, y equals log base 2 of x plus 2. Okay, well really all this is we're just going to shift it up by 2 units. That's what that means. If you're adding 2 to the end, basically what that's telling you is that you have this y is log base 2 of x, and then I'm going to take that y value and add 2 to it, so everything goes up by 2. But let's just go ahead and do it using all of the steps that we did before. So the first thing we want to do is we want to find the domain. So the domain is all of the x's such that the argument is greater than 0, but the argument is just x greater than 0. So the domain then is the set from 0 to infinity. The range, we know that the range of log base 2 of x is from negative infinity to infinity, so if you add 2 to it, that doesn't change it. So the range is negative infinity to infinity. Okay, so what about the vertical asymptote? Well, the vertical asymptote happens at the left endpoint, which is 0, so it's going to be at x equals 0. So we're going to have a vertical asymptote right here. Okay, now we want to find the x-intercept and the key point. So the x-intercept, of course, that's where y is equal to 0. So 0 is the power of 2 that gives us x plus 2. So 0 is the power of 2 that gives us x plus 2. So subtract this 2 from both sides. So we get negative 2 equals log base 2 of x. So negative 2 is the power of 2 that gives us x. So what does that mean? That means 2 to the negative 2 equals x. So 1/4 equals x. So the x-intercept then is 1/4, comma, 0. So this point right here is 1. So 1/4 is right about there. So it's quite close to the x-axis. It's even a little bit closer. That's right about there. So that's our x-intercept. What about our key point now? Key point. That's where y is equal to 1. So 1 is equal to log base 2 of x plus 2. So again, we subtract 2 from both sides, and we get minus 1 equals log base 2 of x. So negative 1 is the power of 2 that gives us x. So 2 to the negative 1 gives us x. So 1/2 is equal to x. So that means our key point is 1/2, comma 1. So 1/2 is right here. It's right here. And so this is when y is equal to 1, which is right there. Okay. So that's our key point. So here we have our x-intercept, and here we have our key point. And now we just connect the dots, being sure not to pass through this vertical asymptote, because we know that the end behavior is that as x moves closer to the vertical asymptote, you're going to get negative infinity. So it's going to look something like that. Now, once again, I've done this on a computer, and it's on the next slide so we can compare to see how we did. And there we go. Not too bad. If you wanted to be more precise, you could try to compute extra values on the curve just to get a better idea of the shape. Let's do another one. For this one, once again, we're given the graph of y equals log base 3. So that's this one, y equals log base 3 of x. And now we're asked to find the graph of y equals log base 3 of x minus 2 plus 4. Again, we can think of this one in terms of shifts. This x minus 2 tells us to shift to the right by 2, and this plus 4 tells us to shift up by 4. Okay, but let's go ahead and do this as we've been doing it. So the first thing to do is to find the domain. The domain is the set where this argument is positive. So we want x minus 2 to be greater than 0. Or in other words, x is greater than 2 if you add 2 to both sides. So that means our domain in interval notation is the set from 2 to infinity. So that tells us we're going to have a vertical asymptote at 2, like so. Really, I should put that in later, but I just did it now anyway. The range is the set from minus infinity to infinity again. And now we have the vertical asymptote, which is x equals 2. So now is when I'm supposed to put it in, but I've already done it. Okay, the vertical asymptote, keep in mind, is just the endpoint of the domain. Not the infinite endpoint. There's no vertical asymptote there. Okay, so now we want to find our x-intercept. And again, that's the point where y is equal to 0. So we want 0 is equal to the log base 3 of x minus 2 plus 4. So our ultimate goal is to solve for x. But that x is buried inside of this logarithm, so the first step is to solve for the logarithm. So we subtract 4 from both sides. So negative 4 is equal to log base 3 x minus 2. So negative 4 is the power of 3 that gives us x minus 2. So 3 to the negative 4 is equal to x minus 2. Well, 3 to the negative 4, that's 1 over 3 to the 4 equals x minus 2. So add 2 to both sides, and we get 1 over 3 to the 4 plus 2 equals x. So we'll probably need a computer to help us actually compute the value of that, but you can see that the x-coordinate is just slightly bigger than 2. So the x-intercept then is, so this gives us an x-intercept where x is equal to 2 plus 1 over 3 to the 4th, comma 0. So if we use a calculator to compute this value right here, this should give us 163 over 81. So, but what's really important is that that's just slightly bigger than 2. So if we go to our graph, slightly bigger than 2 would put it right about here. Okay, so that's the x-intercept. We want to do the key point now as well. So key point. Now the key point is where y is equal to 1. So it's going to be a similar computation to what we just did. So 1 is equal to the log base 3 of x minus 2 plus 4. So you subtract 4 from both sides, and you get negative 3 equals log base 3 of x minus 2. So negative 3 is the power of 3 that gives you x minus 2. So 3 to the negative 3 equals x minus 2. So that's 1 over 3 cubed equals x minus 2. So in this case, x is equal to 2 plus 1 over 3 to the 3. And again, we'll need a calculator to help us compute this, but this is 55 over 27. Okay, so the key point is where x is 2 plus 1 over 3 cubed, comma 1. Now again, this value is only slightly bigger than 2. This is only slightly bigger than 2, but it's also slightly bigger than our x-intercept, because here it's 2 plus 1 over 3 to the 4th. 1 over 3 to the 4th is smaller than 1 over 3 cubed, because 3 to the 4th is bigger than 3 cubed. So this value is just slightly bigger. So this is when y is equal to 1, which is right here. So x is just slightly bigger than what it was for the x-intercept. So it's going to put us like right about there. Now we don't want to forget that we have a vertical asymptote here at x equals 2. So it's going to be very tight here. It's going to be like something like that. Maybe, let me just try it again. Something a little bit like, there we go. So, and then it's going to go something like this. Okay. So this is y equals log base 3 x minus 2 plus 4. And once again, we can compare to a computer-generated graph on the next slide. And as you can see, it's not that bad of a drawing that we did. So this one is y equals log base 3 of x minus 2 plus 4. Quantity x minus 2, and then we add to that 4. There we go. So let's do one more. Example 5. Use the graph of y equals log base 10 of x to graph y equals 5 times log of 2 minus x. So the graph that you see here is y equals log base 10, or just the common log, or just log, L-O-G, y equals log of x. Now, we want to use this graph to help us graph 5 times log of 2 minus x. This one's going to be a little bit more involved, because what you can see here is that this one has a minus in front of the x. So if you have a minus in front of the x, that means you're going to have, at some point, a reflection through the y-axis. So now our logarithmic function is going to end up going in sort of the opposite direction from the way that we might usually have them. We'll approach this problem the same way that we did the others, so we're just going to do the same steps. So we'll start with the domain. The domain is where the argument of the logarithm is positive. So 2 minus x is strictly greater than 0. So now we're going to add x to both sides. And then we have 2 is greater than x, or in other words, x is less than 2. So now we see that the domain is going to be the set from minus infinity to 2. So in particular, that means we're going to have our vertical asymptote at 2. But you can see that in this particular case, the graph of the logarithmic function is going to be to the left of the vertical asymptote. It's going to be the left of 2. So 2 is here. So that's our vertical asymptote. And our domain is the set of all numbers less than 2. So that means the graph is going to be over here. It's going to be to the left of the vertical asymptote. Now the range is still going to be the set of all real numbers. So minus infinity to infinity. And the vertical asymptote we've already mentioned is at x equals 2. Now in order to actually graph this, what we're going to do is we're just going to find the x-intercept and the key point just in the way that we have before. So the x-intercept is the place where y is equal to 0. So we have 0 is equal to 5 times log base 10 of 2 minus x. So we can divide everything by 5, and we just end up with 0 equals log 2 minus x. So 0 is the power of 10 that gives us 2 minus x. 10 to the 0 equals 2 minus x. 10 to the 0 is 1. So 1 equals 2 minus x. Subtract 2 from both sides, and we get minus 1 equals negative x, or 1 equals x. Consequently, our x-intercept is where x is equal to 1. So the point itself is where x is equal to 1 and y is equal to 0. So that's right here. Notice that that's the x-intercept of our parent function, y equals log x. Okay, now we want to find the key point. Now the key point is where y is equal to 1, so it's the same sort of thing. 1 equals 5 log 2 minus x. Now we divide by 5 and we end up with 1/5 equals log 2 minus x. That's supposed to be a 2. Let's try that again. 2 minus x. So 1/5 is the power of 10 that gives us 2 minus x. So 10 raised to the 1/5 power equals 2 minus x. So now we can add x to both sides. So then we have x plus 10 to the 1/5 equals 2. And now we just subtract this 10 to the 1/5. So we're going to get x is equal to 2 minus 10 to the 1/5. Now in the last example, we might have been able to get away with doing those without using a calculator, but here we need the 5th root of 10. So if you use a calculator, this is approximately 0.41. So that means the key point has coordinates 0.41, comma 1, or at least approximately. So that's going to give you, so here's 1 on the y-axis. So we want just a little bit under a half. So if this is half, it's going to be right about here. Now we want to connect the dots. So it's going to look something like that. And once again, we can compare it to the actual graph obtained by a computer on the next slide. And there we have it. So not too bad.